Hello, my name is Boris Pismenny, and this talk is about the benefits of general-purpose On-NIC memory. It is a joint effort by researchers from Technion, Aviv University, VMware Research, and NVIDIA. In this work, we make an optimization to NICs that helps with a class of applications which we call data movers. Data movers are applications that are network intensive, process message metadata, and send or receive message data untouched. There are two main types of data mover applications. First, there are applications that process packet headers, but not packet payload, such as network functions like routers, NAT, load balancers, and multicast applications. Second, there are applications that associate item key with item data, such as key value stores like memcached and static web servers like Apache. In this talk, we focus on the first class, and in the paper, you can find details about the second class. Next, we use an example to demonstrate the cost of data movers. Consider a software router receiving a packet. The router often receives packets with small headers and large payload. When the packet is received, it is transferred by the NIC over PCle to the host CPU. Thereafter, the routing application inspects the packet header. Specifically, it looks at the destination IP and compares it to entries in the routing table, where it looks for the most appropriate match. Once the most appropriate match is found, it determines the packet's new MAC header. But the exact details of this processing are not important here. What matters to us is that the data is not part of them. Once this is done, the packet is sent out to the wire. And this requires the NIC to DMA the entire packet from memory, including the data, even though the data was not involved in the processing. The main point is that in this process, we waste resources on the data, both in transmitting it to the wire and receiving it, even though the data was never used by the host. So in summary, data movers waste PCIe and memory bandwidth when moving packet data through the system, and possibly waste CPU cycles when copying the packet's data inside the host. Additionally, if the system is equipped with direct cache access technologies such as Intel DDIO, then NIC DMA reads and writes are serviced by the last level cache. And this wastes last level cache space and bandwidth in the process. So our idea is to eliminate the cost of moving message data by leaving it on memory inside the NIC. We call this memory Nicmem. At the same time, we pass message metadata to the host for processing. By doing this, we avoid the costs associated with data movers. Today's NICs contain internal SR memory, just a few megabytes, for stateful offloading, such as RDMA, packet steering, and SRIOV. When stateful offloads are not used, this memory is underutilized. For example, recent Mellanox NICs utilize only 15% by default. By the way, Mellanox was purchased by NVIDIA, and so we call this NVIDIA NICs for the rest of the talk. Finally, it is possible to enlarge this memory at relatively low prices. A back-of-the-envelope computation shows that it takes about 20 cents per megabyte at estimated 7 nanometer wafer prices. And technologies such as 3D stacking can further reduce LNM cost. We expose Nicmem to software as memory mapped I/O. This allows applications to treat Nicmem as regular memory. Applications can map it to their virtual address space and dereference it via pointers to read and write. For example, an application that does packet processing can use the following data structure to represent a packet, with a pointer to the header and a pointer to the data, and both point to data in host memory. Now, to use Nicmem and to avoid the cost of data movers, all that is needed is to point the data to Nicmem. The main point is that Nicmem is mostly just like regular memory from the application's perspective. Next, we show how to leverage Nicmem to mitigate the costs of data movers in network function virtualization applications. We focus on the DPDK framework as it is common in NFV applications. So first, we describe how DPDK processes packets today when only hostname is available. So when a packet is received by the NIC, it selects a queue to process that packet, a receive queue. It goes and reads a descriptor from the receive queue, which points to a buffer. Thereafter, the NIC stores packets data in that buffer and lets the host to start processing it. So this is step one. In the next step, the network function inspects the packet's headers and optionally modifies them. And when it's done, it writes a descriptor to the transmit queue of the NIC and rings the doorbell. Thereafter, the NIC reads the transmit descriptor, which is step 3, and finds the pointer to the buffer, the packet's data, and DMA reads the packet's data to send it over to the wire. And this process is wasteful as it wastes PCle and memory bandwidth in the process. So our proposal with Nicmem is to split packet headers from payload and to store the payload on NIC memory. And this is illustrated by the following transition. So we take the payload and move it into Nicmem. And now we also need to get the headers into hostname. So we use an additional pointer to point to hostname. And this is how we work with the Nicmem approach. One thing to notice here is that we require 2 pointers per descriptor, and we find that the processing of those 2 pointers per descriptor is wasteful because both CPU and NIC require the processing of those 2 buffers. We therefore propose an additional optimization called inlining, where we write the packets header data inside the descriptors themselves. And this allows us to get back to a single pointer per descriptor. And this is illustrated as follows. So now we have both from the receive and the transmit descriptor a copy of the packet's data. This approach adds some CPU overhead to copy the data into the transmit descriptor, but it benefits from using one descriptor. We implement support for all of these approaches in NVIDIA's ConnectX 5 driver inside DPDK and expose it to applications. So we mentioned the costs associated with data movers, but are these issues real? Do they happen in practice, or is it possible it's just theoretical? The next few slides will show a bottleneck in the NIC, in PCIe, and in memory bandwidth experienced by network function applications. Let's start with a NIC bottleneck. Here we run a DPDK layer 3 forwarding on a single core and load it with 100 gigabits per second. We compare hostname with Nicmem and see that the throughput of hostname is lower than the throughput of Nicmem. Additionally, the latency of hostname is much higher than the latency of Nicmem. When we investigate and try to understand why do we observe these results, we find that the hostname transmit queue is overflowing and causing packet loss on the software side and increases latency. Now, Nicmem avoids this issue because its packets, which consist of only headers inside the host memory, consume less space in a bottleneck buffer inside the NIC. You might think that this is a bug, but NVIDIA engineers confirm that the issue is real and it is unlikely to get fixed, as NICs are not built to provide line rate with a single queue. Now, to observe a PCIe bottleneck, we again run DPDK layer 3 folding, but we use 2 cores instead of 1, which allows us to use 2 queues and therefore avoid the NIC bottleneck. So when running with 2 cores, we see that both Nicmem and hostmem achieve line rate throughput. However, the latency of the hostmem is about 3 times higher than the latency of Nicmem. When we look deeper into this, we find that the PCI traffic towards the host is at 100%, which stalls packet processing and increases latency. Nicmem avoids this issue because it transfers only packet headers over PCle. Therefore, it is not bottlenecked. Last, we show a memory bandwidth bottleneck. So now we run DPDK layer 3 folding on 8 cores, and we use 2 NICs with 200 gigabits per second to load this application. Additionally, to make layer 3 folding more memory intensive, we add 250 memory accesses to the packet's data path. And so now when we look at the results, we see that hostmem throughput is about 15% lower, and its latency is about 10 times higher. The reason is that the memory bandwidth experienced by hostmem is around 40 gigabytes per second, and this slows down the processing of packets in the hostmem-based application. To understand why memory bandwidth slows down the application, we measure our CPU's memory latency as a function of memory bandwidth. And we show the result in the following figures. So what we see is that memory latency increases linearly with memory bandwidth at first, but then it increases exponentially as memory bandwidth approaches the system's capacity. Now, even though we are not close to the system's capacity now, we are still experiencing increased memory latency for accesses, and therefore the hostmem-based application performs poorly. Nicmem is able to avoid all of this because only packet headers go to host memory, and therefore the memory bandwidth imposed by it is lower. So we already demonstrated that Nicmem is a good idea. Now let's take a look at some additional experimental results. We first showed that Nicmem improves scalability. Then we see that Nicmem complements DDIO. And finally, we show how Nicmem outperforms NFV acceleration in NIC hardware. Okay, so to show scalability, we run a fast-click NAT-based network function, and we load it with 200 gigabits, while we vary the number of cores. And so, as we can see in the results, both throughput and latency, hostmem never achieves line rate. What happens is that initially, hostmem throughput increases linearly, but it starts to decrease until eventually it stalls, and the throughput is the same between 12 and 14 cores, which are the last two measurements. The reason this happens is because the DDIO hit rate of hostmem decreases as we increase the number of cores. And decreasing DDIO hit rate causes memory bandwidth to increase significantly, and it hurts application performance, as we saw before. In contrast, NIC memory throughput scales and achieves line rate at about 12 cores, which significantly improves latency. Now let's take a look at DDIO. So we repeat the experiment from the scalability slide, from the previous slide, where we ran fast-click. Now we run it on 14 cores, which was the maximum. And again, load it with 200 gigabits per second. And we vary the number of DDIO ways exposed to the application. By default, only 2 ways are exposed to applications, but previous research has shown that increasing the number of DDIO ways available to network-intensive applications is beneficial. And indeed, we see that hostname improves its throughput at first gradually, and then it achieves line rate. When it achieves line rate, it also significantly improves its latency. And all of this because the DDIO hit rate is greatly improved as we increase the number of DDIO ways available to the application. And this improves memory bandwidth, which improves performance. And nevertheless, when using Nicmem, we can see that latency is still 4 times lower, even with the maximum DDIO capacity. And memory bandwidth is also twice lower. In a sense, Nicmem is a better alternative to DDIO, as it avoids both the memory bandwidth and PCIe bandwidth experienced by the application, without any contentention on the last level cache. Okay, so finally, let's take a look at Nicmem compared to NIC acceleration. So before we had Nicmem, which stores packet payload inside the NIC memory, the main use of On-NIC memory in NFV applications was to store per flow state for hardware acceleration. So to compare Nicmem to NIC acceleration, we implement a simple network function that counts the number of packets and bytes per flow. And we run it on two queues. We choose two CPUs when using the CPU. And we implement this on DPDK with hostmem, Nicmem, and with ASAP, which is NVIDIA's accelerated switching and packet processing technology that completely offloads all the network functionality into the NIC hardware. And as we can see, when the number of flows is low, ASAP achieves the best performance. It's completely idle. It achieves line rate throughput, and it has the lowest latency. However, as we increase the number of flows, at a certain point, we see that the latency of ASAP spikes until it becomes worse than both Nicmem and hostmem, and its throughput drops dramatically. The reason is that the NIC's cache overflows, and it cannot keep this number of flows inside the NIC. And as a result, performance plummets. And here we show the number of NIC cache misses experienced. So the NIC is able to hide some cache misses, but at a certain point, it's just too much. And Nicmem and hostmem do not suffer from this effect because their performance is not dependent on the number of flows, as the payload being stored is not per flow. And as a result, Nicmem and hostmem avoid this issue regardless of the number of flows. Finally, I'd like to discuss some practical considerations. So today's NIC memory is small, and DPDK's per core queues consume about 1.5 MB per core. As a result, it may not be possible to use Nicmem for all DPDK queues. We therefore run an experiment where we use, again, FastClick's NAT application on 14 cores, but we vary the number of Nicmem queues. So when there are no Nicmem queues, so 0, latency is high and throughput is relatively low. But when we use even a single Nicmem queue, we are able to greatly improve both throughput and latency. The reason is that the single Nicmem queue already helps avoid the PCA bottleneck. Then we measure the performance when we use Nicmem for all queues. And here we see that it improves the memory bandwidth, and this improves latency further and also improves throughput. So in conclusion, Nicmem benefits data mover applications, specifically by eliminating NIC PCIe and memory bandwidth bottlenecks. Nicmem also complements DDIO and outperforms NVIDIA acceleration in hardware. Finally, even though Nicmem is small, even a single Nicmem queue can help improve performance. Thank you for listening.